Data Centre is a clearinghouse for all of Canada's astronomical data. So the data comes to the various telescopes, comes here to Victoria, and then it gets sent out to people who want to use it. Now, earlier this week, the very boring side of astronomy, I was in a telecon, and I have a lot of good telecons, but this is not one of them. And my daughter's friend was in earshot, and she was listening to us discuss not astronomy, not all the great computers that we buy to do astronomy, but the financing, the accounting for all these computers. And at the end of it, like I have this meeting every couple of weeks, and it's only an hour, but with her, this woman in earshot made me realize that perhaps at some point I had made some poor life choices. So I'm not going to talk to you about the 25-26 fiscal year Q3 activities expenditure report, but I am going to talk about the stuff that gets me out of bed in the morning and gets me into the office. I've put up this poem from Walt Whitman from 150 years ago that I think of every single time I give a talk to non-astronomers, and actually to astronomers as well. Let's not lose focus what's important. So I'm going to talk about two, so there's my quote on the other side, two wide field imaging surveys where people are taking pictures of the large fraction of the sky and how that's not really a new thing, but they're two big projects that Canada is involved in that are actually run out of the US and out of Europe that Canada is now a part of. And I'm going to talk about, talk a little about those things, a little bit about the science, and then talk about what actually interests me from both of those things. So we'll start off with some cool pictures. And the question is, I'm going to show you three pictures, and I'm going to ask you which is the most interesting one. So this is the Horsehead Nebula, so gas, dust from, and this is seen by the Euclid Space Telescope. And then here's a cluster of galaxies as seen by the very new Vera C. Rubin Observatory. And I'm going to show you my favorite picture, this one here. And you go, why is this one the most exciting? First off, the first picture has been seen literally 1 billion times by hundreds of millions of people have looked at it over the years. And the second one just came out a couple of weeks ago, but it's already been seen by tens of millions of people. Up until a few minutes ago, this picture had only been seen by one person, me. It's now been seen by 40 people, so 41 people total. And why is this picture so cool? It's because in this picture is everything in astronomy. So anything that's sort of point-like, anything that's just a dot, that's a star. Anything that's sort of extended and fuzzy, that's a galaxy. And here's this picture, and then the picture that was taken 10 minutes before, whoop, and beep, boop, beep, boop. Up in the top left corner are a couple of asteroids. And if you look closer way down here, there's another one. Come on. All right. So there you go. That's all of astronomy in two pictures. Okay? And it has the advantage of well, it was mine, and now it's ours. Like it's sort of much more intimate, I think. So, okay, let's talk about the two projects. So the first is, okay, who here has heard of the Hubble Space Telescope? Everybody. Who here has heard of the James Webb Space Telescope? Who here has heard of the Euclid Space Telescope before I put this picture up? 3 people, 4, 5, okay. So the Euclid Space Telescope launched a couple of years ago. It's run out of Europe, which doesn't have quite the PR machine that NASA does, which is why you haven't heard of it. It took that first picture of the Horsehead Nebula. And this is sort of, this is not one of the official pictures of it. This was taken by a colleague of mine. There he is, sort of standing up. Looks like a good space telescope, just sort of standing there. And so it launched. It's out in space now. It's taking data. It's compared to Hubble or James Webb. The size of the primary mirror, which is a measure of the light gathering power. So Hubble's kind of a human-sized telescope. Euclid is a little bit smaller than that, and then of course James Webb is this huge 8-meter thing. So compared to those other two, it's not as impressive until you look at the camera. So these are the footprints of the cameras from Hubble and JWST, and this is the footprint for the primary camera of Euclid. This huge, massive thing, and the reason for that is trying to make a map of the whole sky, not just a little pencil beam. surveys. So it doesn't go as deep as Hubble because it doesn't have as much, and James Webb, because it doesn't have as much light collecting power, but it's able to look at everything eventually. So there's a picture of the camera. Sort of physically, it's about this big. The fact that it's blue is because it's actually a red sensitive camera. So all the red light gets absorbed by the camera and doesn't see it. You just see the blue light which bounces off it. Okay, so what's Euclid looking for? So it actually has, all these things have kind of a laundry list of science goals. I'm not really going to go into all of them in great detail, but the main thing is it's looking for weak gravitational lensing. So weak gravitational lensing, you've heard of black holes and how they suck everything, including light, into themselves. That's the extreme form of this. But fainter things, sorry, not fainter things, less massive things still bend light. Everything bends light, it's just a question of degree. And so this picture shows the original shape of the galaxies in kind of this blue teal color. And then after it's been gravitationally lensed by some dark matter that's sitting between us and those galaxies, the galaxies get distorted ever so slightly. But you can't tell necessarily. I'm going through this really fast because it's not what I care about the most in all of this, but I just sort of want to give a flavor of all these little bits and pieces. It gets distorted, and you can figure out where the dark matter is. And there are some people who love the math that goes into this. It's incredibly complicated, and it requires massive statistics because the distortion is dramatically exaggerated in this picture. It's actually the difference between this and this. Like, it's just this tiny effect. But if you gather enough galaxies and measure enough distortions, you can build up a map of the dark matter. So I'm looking forward to the map of the dark matter, but the actual process of making that map is someone else's job. But the other thing it did, so sometimes these are kind of the weak gravitational lenses, but there are also cases where, but much less common, where it's strong enough that you can see the lensing happen just by eye. You can immediately see that there's a strong, dark, invisible mass that is lensing the galaxy behind it. These are very rare, but if you look at enough of the sky, you're going to find lots of them. So this following, this is how you sort of an illustration of how you can see something that isn't there by looking at what's behind it. So here is a picture of some windows through another window made of that old wibbly glass that you don't see very often. You can see it's distorting what's going on behind it. So you know that there's something there, even though you can't see it, because it's distorting what's happened behind it. So the strong gravitational lenses, let's see if this movie works, which it probably may or may not. This is gravitational lenses seen from the ground and then from Euclid. And you can see that because it's above the atmosphere, you get a vastly sharper picture of what's going on when you look at it from space. So you can see all those arcs, and those arcs are, stop. You saw those arcs, which were the effects of the gravitational lens. And so Euclid, if it took a tiny fraction of what it's going to have over its 6-year mission, and already we found a whole bunch of these strong gravitational lenses, which basically double already the number of ones that were known. We've also found cases where there's 2 lenses. So there's a galaxy that's being lensed, another galaxy that's doing the lensing, and a third galaxy that's also doing the lensing. So you have this chance alignment, and you only get these if you kind of look over and over and over again at lots of different parts of the sky to find them all. Okay, so next slide. Yeah. Okay, now I'm going to change to another telescope. So this is the Vera C. Rubin Observatory, which is just coming online now. It had its first kind of data release a couple of weeks ago. And again, it's a tiny fraction of what the data will be that will be released in later next year, and then the year after there'll be a series of data releases. And so this is a very strange-looking telescope. It's huge. Okay, so I mean, this is where a person might stand. Okay, compared to the telescope in the dome, it's about the same length, but it's just as wide. Like the one in the dome is kind of a long, skinny affair, and this one here is about as wide as it is long. It's this incredibly compact telescope, and the reason it's compact is because it is taking essentially a movie of the sky over the years. And it has to do that, it has to change where it's pointing over and over again. And if you had something long and skinny, you turn and it would do this, turn and it does this, turn and it does this, and it would wibble. You'd have to have this settling time each time you moved it, and you have to move it, in fact, every 20 seconds. When this thing is in operation, no one's allowed in the dome, because unlike, I don't know if you've seen the telescope over here, you've had the tour and seen it sort of moving around. You can be in the dome, and if the telescope's coming for you, you can kind of shuffle slowly to one side. No one can outrun this when it's in full operation, let alone outwalk it. So the dome has to be cleared before they actually put it into operation. It's huge, so this gives you a much better idea of what the primary mirror looks like. So that's the guy in the Hawaiian shirt at the center is the director of the, now the director of the Rubin Observatory, and a crowd of people around it. So it's just this massive giant mirror that collects light. And then a massive giant camera. So this is the lens, the front lens of the camera, and that's a person standing beside it to get for scale. And then this thing over here, and again, there's a person in the background. This is all the electronics that go into it. So if you look on the telescope here, that whole unit is about this big, and this thing here is about the same size as the whole telescope. It's this truly massive piece of machinery. In terms of field of view, so here's Hubble, James Webb, Euclid, and now that's the field of view of the Vera Rubin Observatory. It's this massive, massive thing. And then it's actually made of, like one of these is roughly what might go into your digital camera on your phone. And then there's 9 of them grouped. They're grouped in 9 by 9, and then this huge, huge array of pixels. So LSST is the Legacy Survey of Space and Time. Originally, the telescope was called the Large Synoptic Survey Telescope, so LSST, and then they renamed the telescope the Vera Rubin Observatory, but they named the survey the Legacy Survey of Space and Time, LSST, so they could keep the acronym, even though it meant something different. The simple version of it is it's going to look at the same sky over and over again every 3 nights. It's actually a bit more complicated than that. See if this movie plays. It observes in this incredibly complicated pattern. So the whole thing is moving around because the sky is moving, and then the thing that's being drawn is the where it's mapping. When you can't see it, the dot, it's because it's going back to somewhere it's already been to look at it a second time. And so it's actually this very complicated cadence of how they observe the sky. So sometimes it observes over and over again on one spot because they're looking for supernova. Sometimes they observe every night or so because they're looking for asteroids or other things like that. And then sometimes every few weeks if they're just trying to make a static map of the whole sky. No, that's not what I want to do. I want to do this. So what's it looking for? So night by night, it's looking for supernova, asteroids, that thing we don't know about yet. And then, but what it does, it takes the images, then it compares to what it was last time we looked at it, and then subtracts that, and then you get the difference image, and the difference says, okay, that thing got brighter, or that thing moved, or that thing wasn't there before. That's something interesting. At the end of the year, you take all the data and you add it all together, you make one super deep image. So let's talk about that for a bit. So here's another movie, and they stole my idea because I made the other slide years ago. But here is kind of the same thing as that first slide of mine, but somewhat more professionally prepared by people where they're looking for asteroids. And it kind of speaks for itself. So there's a new asteroid, observe it, it moves across the sky. Oh, look, there's another one. Oh, look, there's 3. Oh, look, there's a lot. Oh, look, there's like really a lot. And this is just sort of one night. And then, okay, now we're just going to have a movie of all of them slowly moving across the sky. And again, this is a very small patch. This is not even the full camera. And then each night they discover a new one, gets added to the collection, and they're all slowly moving across the sky. And then we move to the part of the movie Zoink, where now as seen in the solar system, and the ones that are highlighted are the ones that were discovered in one night with the non-complete camera, and then the faint halo is all the stuff that's left to be discovered. It's a simulation. Come on, there we go. The other thing it's going to do is when you get all the data put together, you can look for stellar streams. So this is a map of our galaxy as seen from inside the galaxy. So it's not perhaps the traditional way, well, it's what you would see if you were to go out and look at night with the right kind of eyes. If you look at the stars and you look at their colors, you can see that these streams, these are the ones that are known already, but Ruben's going to find a lot more of them. Streams of stars that all have the exact same color. And that is because they are from small satellite galaxies that encountered ours and got ripped apart from a blob and stretched out into this long stream. And so if you look at it from sort of the outside, the God's eye view, this is what the map looks like. So we're in the middle, and then there's all these streams around outside us. Okay, so that's, none of this is, this is going back to, what the learned astronomer was talking about. This is, these all-sky surveys are not new ideas. Starting in the 2nd century BC, there was this fellow called Hipparchus who made a list of all the stars and wrote it down. And then there's a second version that came out 4 centuries later, and that's a copy of it that you can see here, actually a translation of the thing. The original star catalog they thought was lost, and as I was Googling this the other day, I discovered that in fact they found a copy that had been, someone had reused the paper, scraped it all off and written something else on top of it, but if you looked at it with the right kind of image focusing, you could see that behind it, is the red lighting, was actually a list of stars that someone found and written down at a much later date. So anyhow, this idea of surveying the whole sky is not a new one. It's just sort of bigger and better now. So here's the laundry list again of both telescopes put together. And then the one that I'm quite interested in is the things that aren't planned yet. Both these telescopes are discovering something, I suspect, who knows, that no one's ever thought of before, that's not planned for. So that's going to be fun. But what gets me out of bed is pictures like this, which don't have any particularly large, bright thing in the middle that catches your eye, and that's why they never make press releases with this kind of image, because it doesn't, without a whole bunch of explanation, like the 20 minutes I just spoke, you can't figure out why this is interesting. But this is a random star field as seen by Ruben with lots of colors. And this is a random star field as seen by Euclid with not quite as colorful, but much, much sharper because it's taken from space. And then the version that I like, both of these you can see on the web, is actually the raw data directly from Euclid. And the reason the background looks staticky is because there's only about 10 photons coming from. The sky is so black that you're only seeing about 10 photons. If you're not seeing 10 photons, you're seeing 10 plus or minus 3. So the white sparkles in here are 3 extra photons, and the darker areas are places where there just slightly fewer photons showed up. And then on top of that, you see all the galaxies, the stars, and presumably some asteroids, although I don't have an image to blink with in this case, all together in one spot. And again, these things aren't going to be, these surveys are so large that no one actually has time to look at all the pictures. So if you can go to a website and look at it, you can probably be the first person to actually look at that particular star, that particular galaxy. And that's what I find fun. It's not the science, it's actually sort of a more aesthetic Walt Whitman thing. And it's the same thing as when you look up at the sky, right? It's black with white dots, right? That's what we do, what we see when you look up, and it's beautiful. And again, if you look at get a really powerful telescope, you can see the same thing, except much, much, much deeper. So here we go with Walt Whitman's quote again, but I'm just going to leave up. All these things are on the web. If you're interested, take a picture of the screen. And then there are all these websites where you can go and look at all these pictures of that people have from all these surveys. The second top one there is going to look like 2008 for up on your screen, because that's when I wrote it. And the other ones are a little bit more fancy and more modern looking, but the pictures are what is important, not the display. Thank you very much.